Hello everyone, today we will be talking about reference tracking and McMillan's degree. In this video we will be going through some of the basics of both reference tracking and McMillan's degree, and we will be looking into some of their examples such as their usage in motor tracking, some of the usage in navigation systems, and etc. Reference tracking is used to bring our output value close to a desired output value. This desired output value is usually taken as a reference, and we're supposed to bring down the error between the two to zero. A system with good reference tracking will have an error of 0 where the output will follow the reference exactly, and the system with bad reference tracking will not have an error of 0. In our example that we will be looking at an example of a motor where we will be using a scaling constant to bring the value down to 0. Final value theorem is used to find the final value of a system when time tends to infinity or when s tends to 0 in the s domain. The right half planes are usually not preferred as the system never converges to a value and it diverges, and it's impossible to find the final value of the system. In the graph shown below, this graph is between the output and the time. We can see that when time tends to infinity, we have a converging value for the output. So we can find a final value for this given graph. Usually two checks are performed to confirm whether the final value theorem is valid or not. There are some cases where the final value theorem is not valid. So the two checks that are usually performed in control theory are, one is that the non-zero roots of the denominator must have a negative real part, and the second one is that we must not have more than one pole at the origin. A system with a perfect reference tracking will have a steady state error of 0, that is, the output will perfectly track the reference value. But if we are given a system that does not have a perfect tracking performance, we can find a scalar value such that the error is minimized to 0, and this method is called reference scaling. Now, if we look at the example shown in this slide, we can see, so the example basically tells us about the trajectory of a space probe trying to leave the planet and trying to reach for some other destination. We can see the red line is the shortest path available, but this is really not practical as the space probe will not be able to store so much fuel for the journey. So usually the path preferred is somewhat similar to the path shown in the green one. So we can see that space probe will leave the planet and will try to take momentum from the sun and maybe from some other planets and then reach the final destination. As you can tell, the perfect tracking of the path is very important for deep space explorations, and if not tracked properly, we are in danger of overshooting or maybe not reaching our target entirely. So reference tracking plays a very important role in deep space navigation, and some of the other examples are its usage in autonomous vehicles, motor speed tracking, and etc. We will be discussing the few examples later in the slides. McMillan's degree is used for minimal realization of the system, which means that we are observing only the states that we're supposed to observe and not unnecessary states. If we're observing more states than we need to, we might increase the number of poles in the system, and that might make the system more unstable or completely unobservable. Now let's look at an example of a motor speed tracking system. Here we will try to track the speed of a motor using state space methods. This slide shows us the state space realization of the DC motor. In this project, the DC motor has been chosen because it gives us a really precise tracking. And we can see that omega is the angular velocity, I is the current, and U is the input voltage. Here J is the mechanical inertia, Kc is the back EMF, Kd is the damping constant, and Km is the motor torque. R and L are the load resistance and inductance respectively. This slide shows us the feedback loop that we use for tracking omega. Here we can see the usage of 1 by n. Here n is the reference scaling constant to bring the error down to 0 between the actual angular velocity and the reference angular velocity that we want to reach. Here we can see the usage of an amplifier. An amplifier is used basically to give the motor an output voltage. Now the motor takes the input from the amplifier as its voltage and gives us an omega. So we need to control the voltage coming from the amplifier to control the angular velocity of the motor. Here we can see the usage of K. K is the full state feedback controller. Basically what K does is it twerks the value for the voltage coming out of the amplifier so that we can track the angular velocity more precisely and reach the value that we were going to reach. This slide shows us the Matlab code that we have written to realize our system. So we have put in some values for a constant, and then we have realized the system in the state space form using the ss command. Then we have designed an amplifier, and then we have created a plant which has both motor and the amplifier. We have checked the stability of the plant using the isStable command. Eventually we went on to create a feedback, and then we checked its output against a step response. So we were not getting a good settling time, and we were getting some steady state errors. So we tried to find a value for n, which is the scaling constant. Eventually we tried to find the response against another step response, and this time we got a better value and zero error. This slide shows the tracking results of the motor against step responses. The slide on the left hand side shows us the tracking result when the scaling constant was not applied, and the slide on the right hand side shows us the tracking result when the value for n, that is the reference scaling constant, was applied. You can see from the graph on the left hand side that the final value never quite reaches 1, whereas it reaches 1 on the graph shown on the right hand side. That is the value we were looking for. This goes to show that when we're not using the scaling constant, we will never quite reach our final value that we're looking for if we have a steady state error. And if we use a scaling constant with a correct value, we will reach our final value in less time, and our steady state error will be reduced to 0. This slide shows us the McMillan degree in our system. We know that the McMillan degree is used for the minimal realization of the system. So to find the McMillan degree, we basically need to find the transfer function of our state space model. So the code on the left hand side shows us exactly that. We realized the motor in the state space model, and then using the ss to tf function, we found the transfer function for our system. And the picture on the right hand side shows us a transfer function, its numerator value and its denominator value. It's quite clear that the denominator has a power of s, that is, s reaches the maximum power of 1, so we can say the Macmillan degree of this system is 1. These are some of the references that we have used for this presentation. These are links to the images that have been used.